Hello, everyone, and welcome to week 2. I hope you're all getting settled into the summer semester, and that you found my course materials easy enough to navigate. Again, if you have any questions at all, please reach out via email or set up an appointment, and we can meet on Zoom. This week, we're going to discuss both chapters 3 and 4. And chapter 3 is on matter and minerals. And I listened back through my presentation last week, and it's kind of funny. On the last slide, I said matters and mineral. That doesn't make any sense. It's matter and minerals, so I'd like to correct myself there. Anyways, this cave here is a pretty prime example of the massive size that mineral crystalline structures can grow to given enough time. This is it's gypsum. And without further ado, I'll kind of get into the lecture here. So, if you get one thing from this lecture, I want you to understand what the difference between a mineral and a rock is. You would be shocked how many students go through this class and never understand the difference between a mineral and a rock. And if you don't understand this difference, you will be lost throughout the minerals section and throughout the igneous rock section and metamorphic rock section and sedimentary rock section. It's very important. Anyways, it's the end of my rant. What a mineral is basically a naturally occurring, so occurring in the natural world, inorganic, so not made of life forms or organic material, solid, that has an orderly crystalline structure, meaning that crystals are structured in a predictable and known way, and a definite chemical composition, meaning that the mineral is composed of certain known elements. Conversely, a rock is actually a solid mass of minerals or mineral-like matter that occurs naturally. So the difference here is really that minerals are the building blocks of rocks, and we'll get into how minerals form in this chapter, and then ultimately how minerals come to create rocks in the next few chapters. Well, now that you hopefully understand the difference between rocks and minerals, if you don't, please go back to the last slide or review rocks and minerals in your textbook. But now that you hopefully understand that, it's important to discuss what minerals are actually made of so that you can understand how they're created in the natural world, as well as how they might be broken down from forces of erosion, which will be important for later chapters, such as sediment and sedimentary rocks. Well, at the smallest level, minerals are made of atoms. And if you have taken chemistry, this will be a review for you. If not, then this might be new. But all that atoms are the smallest particles of matter that cannot be split, unless they're in a nuclear reactor or the center of a star or something crazy like that. And atoms are composed of protons and neutrons within a nucleus at the center of the atom. And protons have an electrical charge of +1, and neutrons have an electrical charge of 0. And the nucleus with protons and neutrons in it is surrounded by an electron cloud that contains electrons with a charge of -1. And within the electron cloud, the outermost shell, or the outermost area in the cloud, contains what are known as valence electrons. And valence electrons are what interact with valence electrons of other atoms to form bonds, so that atoms can come together to form compounds and more complex structures, and ultimately minerals. So why do atoms actually behave differently from one another? If an atom is the smallest unit that cannot be split, why do they behave differently from one another? Well, it depends on that atom's chemical nature, and specifically it depends on that atom's atomic number. The atomic number is the number of protons in the nucleus of an atom. And atoms that have different numbers of protons in their nuclei have different chemical properties or different chemical natures. These atoms that have different chemical properties or natures are known as elements. So what an element is basically a group of atoms with the same number of protons. So the element hydrogen has one proton, for example. So all hydrogen atoms have one proton, and that gives them a unique chemical nature. There are actually approximately 90 naturally occurring elements. Naturally occurring mean we have discovered them in the natural world, existing on their own. And then several more elements have been synthesized in laboratories. The reason why an element would have to be synthesized in a laboratory and wouldn't exist in the natural world is because some elements are very unstable, and therefore you wouldn't just find them in the natural world, but they still are a group of atoms with a known number of protons that has a unique chemical nature, and we know it to exist because we synthesized it in a lab. And chemists ultimately organized elements into a periodic table so that we can look at elements with similar chemical properties and evaluate how one element might interact with another if they came into contact with it. Well, how exactly do atoms of elements come together to form larger molecules? It's through chemical bonding, and I sort of alluded to it when I was on the periodic table slide, but I'm going to go into it further here. So chemical bonding is the formation of a compound by combining two or more elements. When chemical bonding occurs, it's through the transferring or sharing of electrons that allows each atom in the compound to attain a full valence shell of electrons, or that outer shell of electrons that I've been speaking about. And as I said, this is known as the octet rule, where atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons, or 8 electrons in their outermost shell within their electron cloud. Now that we understand that atoms of different elements bond to one another and why they would want to bond to one another, it's important to discuss the different types of chemical bonds. This is important to understand because different types of chemical bonds happen between different types of elements, or groups of elements, such as metals and nonmetals, for example, and also because different types of bonds have different properties. For example, some types of bonds are stronger than others, and those properties can tell you certain things about the minerals that are ultimately formed by these bonds. The first type of bond that I'd like to discuss are ionic bonds, and these bonds are caused by the attraction of oppositely charged ions to one another. Ionic bonds usually occur between metals and nonmetals. This is because metals have a positive charge and nonmetals have a negative charge, and they want to bond to one another to try to achieve a neutral charge, or to fill their outer shell in the electron cloud with valence electrons. And in an ionic bond, these atoms gain or lose their valence electrons to reach that neutral charge. So if you have a metal with a charge of +2 bonding with a nonmetal with a charge of -2, then in an ionic bond, the metal loses its 2 extra electrons to the nonmetal, so that both atoms can be happy that their valence electrons are full. Ionic compounds that are formed by bonding, formed by ionic bonds of multiple atoms, consist of an orderly arrangement of oppositely charged ions. One example is halite, which is actually table salt, which is NaCl, or sodium chloride, where the metal, sodium, has extra electrons and the nonmetal, chloride, doesn't have enough electrons, and so they bond to one another, where the sodium gives up its extra electrons to the chloride. And this is a diagram showing that exchange where the sodium is losing its extra electrons to chloride, so that both sodium and chloride can be happy that they have a balanced charge and that their valence shell is full of electrons. Another type of chemical bond between atoms of elements is called covalent bonding. And in this case, the bonding happens between a pair of nonmetals rather than a metal and a nonmetal in ionic bonding. And when a bond happens between a pair of nonmetals, a covalent bond happens, the atoms actually share their electrons with one another to fill that outer valence shell of electrons. And this is different from an ionic bond, because in an ionic bond, one atom of an element gives its electrons to another atom of an element that wants those electrons. Both ionic and covalent bonds typically occur in the same compound, because bonds are seldom 100% ionic or covalent. Um, so using the terms ionic bonding and covalent bonding, I'm usually just talking about what the primary type of bonding is within that compound. Another important thing to note about covalent bonding versus ionic bonding is because in covalent bonding, atoms are sharing electrons rather than one atom taking electrons from another atom. In ionic bonding, covalent bonds are significantly stronger than ionic bonds because the atoms really don't want to be moved away from one another when they have to share a pair of electrons. You could think of it as they have to be pretty close to one another for the electrons to actually be around both of the atoms and filling their outermost electron shell, or they're filling their valence electrons to a number of 8. So an example of a covalent bond is a bond between two hydrogen atoms. In this case, you have a hydrogen atom that has one proton and one electron bonding to another hydrogen atom that has one proton and one electron. And the first electron shell, this is maybe a little bit complicated, but the first electron shell only has 2 electrons in it. It's every electron shell beyond that that has 8 electrons in it. So the hydrogen only wants 2 electrons, and one way to get it is to make a covalent bond with another hydrogen atom, because both have 1 electrons, and 1 plus 1 gives you 2 electrons. Then the valence shell is filled and both hydrogens are happy. Another type of chemical bond are metallic bonds. And these bonds, as you might imagine, are bonds that occur between two metals, two elements that are metals in the periodic table. And in metallic bonds, interestingly, the valence electrons, or the electrons in the outermost shell around the element, around the atom, are free to migrate among the atoms within the bond. And this is actually why metals often have a high electrical conductivity. This is, for example, why we use copper in our wires to transmit electricity from one location to another, is because copper allows for this free migration of electrons or electricity to migrate among its atoms. It's important to note that metallic bonds are weaker and less common than ionic and covalent bonds. And then, sort of as I alluded to earlier, many chemical bonds actually exist as hybrids that exhibit some degree of electron sharing and some degree of electron transfer. Sharing being covalent bonding and transfer being ionic bonding or metallic bonding. And so hybrid bonds are the name of those bonds because, as I said, in reality, most bonds they might be primarily covalent bonds or primarily ionic bonds, but they're actually a combination of those things. But for the most part in this class, for simplification's sake, because this isn't a chemistry class, I'll be talking about covalent bonds, ionic bonds, and metallic bonds. This is a diagram of a metallic bond where you can see how the electrons the valence electrons are free to migrate from atom to atom. Again, this is why something like copper is really conductive of electricity. We now know that elements bond to form compounds, and you will come to find out that elements and compounds come together to form minerals. But how do minerals actually grow? How do they form? How do these bonds that occur to ultimately form minerals start to happen? Well, one way is precipitation of mineral matter. This is when ions, so positively or negatively charged atoms, are dissolved in a solution, like water, and the concentration of the ions in that solution reaches saturation, or there are too many ions within that solution. And then crystalline solids start to form. One way that something like this can happen is by a drop in temperature, because if it's hot, then the ions are moving around rapidly and less likely to bond with one another. Or if, for example, water is lost through evaporation. So if you have water that has a lot of sodium and chloride in it, and then water starts to evaporate, eventually the sodium and chloride ions will come close enough to one another that they'll start to bond and form sodium chloride or halite crystals, which is a mineral. This photo here is another example of ions dissolved in solution reaching a saturation point and forming mineral crystals. So geodes like this one that you can see in this diagram form when one silica, which is a compound, is dissolved in groundwater, and that silica precipitates to form quartz crystals, and quartz is a mineral, and these can grow within cavities in the rocks. So this particular type of quartz is called amethyst, and many of you may have seen this in a rock collector's collection, for example. One other way that chemical bonds can start to occur and minerals can start to form is through the crystallization of molten rock, or the crystallization of magma or lava. You can think of this as being a similar process to water freezing. For example, when the magma is hot, the atoms within the magma are very fast and mobile and moving around rapidly because of all the energy from the heat, and then when the magma cools, the atoms slow down because there's less energy available for them, and they begin to bond with one another chemically. One example of crystallization of molten rock happens at volcanoes, for example. If you see a lava flow, that lava is molten rock, and once it gets to the point where it cools to a certain temperature, then the atoms within the lava flow slow down and they start to bond with one another and form mineral crystals and rocks. And then one other way that minerals form, or that chemical bonds occur in nature to form minerals, is through deposition as a result of biological processes or life form processes. One example of this is marine organisms often secrete calcium carbonate. Examples of such organisms include clams and oysters that use calcium carbonate to form their shells. And when you have a bunch of calcium carbonate, which is made of calcium and carbon and 3 oxygen atoms, so when you have a bunch of those elements in the ocean, for example, and then those elements reach a saturation point within the ocean, then they can start to bond, those atoms can start to bond with one another and form the minerals calcite and aragonite, which are both comprised of calcium carbonate. On to the physical properties of minerals. So now that we know how minerals would actually form in nature, it's important to talk about their physical properties because their physical properties are what is generally used to identify them, and the physical properties also determine what the minerals might be useful for in terms of resources for humans, and what the presence of the minerals in geologic materials means for natural processes in the environment. So physical properties can usually be determined by direct observation, just looking at the mineral, or by performing a series of simple tests. And you'll learn to identify minerals in lab this week. So hopefully I can tell you a few things about physical properties of minerals that will help you along when you do this lab with Jeff. One physical property, or one category of physical properties of minerals are optical properties, or properties that you can see just by observation. One of these optical properties is known as luster. Luster is the appearance of a mineral in reflected light. And there are two basic large categories of luster that are metallic luster and non-metallic. As you might have guessed, most minerals that have a metallic luster are metals, and most that have a non-metallic luster are not. Other terms are used to further describe luster, such as vitreous, which is sort of a glassy reflection, or if you imagine like broken glass reflecting light. Silky, I think, is pretty self-explanatory. If light were to reflect off of silk, it might look like that on this type of mineral. Or earthy, which generally means sort of a dull reflection of light rather than a bright and sharp reflection of light. This is an example of a mineral known as galena, where you can see the sample on the left has fresh breaks in it, and it displays a metallic luster. Then the sample on the right doesn't have fresh breaks, and it has seen some erosion, probably by water, over the years, and it sort of tarnished its appearance in giving it what's known as a submetallic luster. And I would venture to say that it also looks a little bit earthy in the sample on the right. What's important to note is when you're using these properties of minerals to identify minerals, you'll have sort of a checklist of yes or no answers. You know, does this mineral have a metallic luster? Yes or no. If it does, then you move on to another set of questions. Another optical property of minerals is color. Now, this is, I think, one of the most important things for me to teach you about identifying minerals in this lecture. Almost every student wants to identify minerals using primarily color. They see the color of the mineral and they think, oh, well, I've seen this color before, it must be mineral A. Well, the problem is that color is generally an unreliable diagnostic property to use for mineral identification. There are a few of exceptions, and I'm sure that Jeff will teach you what those exceptions are, but I want you all to be very careful about the I guess how enticing it is to just use color to identify minerals, and note that you must use the other physical properties of minerals as well. The reason why color is generally an unreliable diagnostic property of minerals is because it's often highly variable for a given mineral, because a slight change in the mineral's chemistry can cause a huge change in the mineral's color in some cases. And in fact, a slight change in a mineral's chemistry often produces gemstones because people think that these minerals are really beautiful, and it's from a slight change in chemistry from another mineral that maybe people would think is ugly. One example of color not being a good diagnostic of a property of minerals is right here. So this figure that I just put on the screen is a bunch of different samples of the mineral fluorite. And you can see that it has the same crystalline structure in each of these mineral samples, but the color varies drastically from sample to sample. The same thing can actually be said for the mineral quartz, which is one of the most common minerals, where a sample of quartz can have a very wide variety of colors, and it's a really bad diagnostic property for quartz as well. Another optical property of minerals is called streak. So streak is the color of a mineral in its powdered form. And you might ask, how would you know what the color of a mineral in its powdered form is? Well, in the lab, you're going to be given what's known as a streak plate, which is basically a flat, very hard surface, and you're going to grind the mineral samples that you have on the streak plate. All of your mineral samples will be softer than the streak plate, so you'll be able to grind them into a powder. And then you use the color of the powder, or the streak color, to distinguish different minerals. So for example, here we have a sample of the mineral pyrite, which many of you are probably familiar with because this is also called fool's gold. And the color of pyrite is like a brass yellow color. However, when you grind it to a powder on a streak plate, the powder's color is actually black, even though the mineral sample itself is sort of a brass yellow color. And you'll see this a lot where the powder is a different color than the sample, which is very interesting, and this is why streak helps us to identify minerals. Another property of minerals that we use to ID them is mineral strength. And one type of strength is hardness. And this is just the resistance of a mineral to abrasion or scratching. So, for example, if you have a sample of a mineral sitting on the table and you're holding it and trying to scratch it with a nail or a penny, do the nail or penny scratch it or not? And if you take the mineral and you try and scratch a piece of glass, does the mineral scratch the glass or does the glass scratch the mineral? These help you to determine what the hardness of the mineral is, or its resistance to abrasion or scratching. When talking about the hardness of minerals, geologists use a standard scale for hardness called the Mohs scale of hardness. And this is the scale right here. So in the uppermost diagram, you can see a number of different types of minerals and their hardness on the Mohs scale. So diamond has a hardness of 10. This plus elaborate marketing schemes is the reason why the saying diamonds live forever exists, or diamonds last forever. And then minerals like talc and gypsum are much softer. On the right, in this top figure, you can see different items that you might use to try to determine the hardness of these minerals. Like your fingernail has a hardness of 2.5, a penny has a hardness of 3.5, and your streak plates have a hardness of 6.5, for example. You generally don't need something harder than your streak plate to identify minerals because quartz is one of the hardest common minerals that you'll come across. Another form of mineral strength rather than its resistance to scratching or scraping, is called cleavage. And this is a mineral's tendency to break along planes of weak bonding. So if you remember when we talked about chemical bonding, how covalent bonds were stronger than ionic bonds, and ionic bonds are stronger than metallic bonds. Well, cleavage planes are planes of weakness in a mineral that are the easiest planes for that mineral to break along. And these planes produce flat, shiny surfaces. And we generally describe the type of cleavage as a number of planes. So you might say one plane of cleavage if you see a number of breaks in a flat parallel surface. Or you might say 3 planes of cleavage if your mineral looks like the shape of a cube, for example. And then the other way to describe cleavage is the angles between the adjacent planes. So sometimes you have a 90-degree angle, that would be like a cubic shape, as I described. And sometimes you have different shapes where the angle of the break is a different angle than a 90-degree angle. So this diagram here shows a number of different types of cleavage. So example A is the mineral muscovite, which has one directional cleavage. So as you can see, these are sort of flat planes where the mineral breaks along. Example B shows cleavage in 2 directions. This is feldspar, and you can see that it looks like this sample of the mineral broke along 2 different planes that are a 90-degree angle from one another. Example C has 2 cleavage planes not at 90-degree angles. Example D, again, this is halide or sodium chloride that we've been talking about a lot in this lecture, has 3 directions at 90-degree angles. So again, this is forming that kind of cubic shape that I was talking about. And then example E has 3 directions not at 90-degree angles. This is calcite. So when we talked about calcium carbonate from the biological organisms such as clams and oysters in the ocean, the mineral that forms from that calcium carbonate is calcite, and it looks like this. And then finally, another example of cleavage is fluorite, which we talked about earlier regarding its color. But fluorite's cleavage planes, or having 4 different planes, is a unique type of cleavage that fluorite has. Another physical property of minerals is specific gravity. And what this really is just the ratio of the weight of a mineral to the weight of an equal volume of water. The average specific gravity of a mineral is approximately 2.7, meaning that the weight per unit volume of the mineral is 2.7 times the weight per unit volume of water. So if you think about holding a soda can in your hand, and then you're to fill that soda can with the average mineral instead of, primarily water, which is the soda, then your soda can would weigh 2.7 times as much, approximately. Other important properties that Jeff will go over in the lab are some minerals are magnetic, so magnetism, a reaction to hydrochloric acid, so calcite that we've talked about a few times here reacts to hydrochloric acid, or it fizzes. Malleability, or whether or not you can change the shape of the mineral by applying force. Double refraction. Taste. Be careful with taste. I'm sure Jeff will talk to you about this, but obviously you can identify halite by taste, but some people might pour acid, hydrochloric acid, on halite thinking that it's calcite, and then you have liquid hydrochloric acid, which is not healthy. So please be careful. And then smell. Some minerals, for example, have an earthy smell. And then elasticity, which is if you are able to change the shape of the mineral, how much does it bounce back to its original position versus stay in the new position that you've bent it towards. Here's an example of, calcite fizzing from putting hydrochloric acid on it, for example. Now moving on from the physical properties of minerals to talking about mineral groups, or different types of minerals. There are actually nearly 4,000 different minerals that have been identified on Earth. Everything solid on Earth that was naturally formed was basically had minerals as its building block. Almost everything solid. So that's important to note. And it's also important to note that you will not have to learn to identify 4,000 types of minerals or anything like that. In the lab and in this class, you'll be learning to identify the most common types of minerals, mostly, because learning to identify those minerals will help you to be able to identify different types of rocks later on in the class, and will also help you to be able to see the world in a different way in terms of how it formed in your everyday life, because you'll see these minerals in your everyday life. So the minerals that you'll be learning to ID in lab are in fact rock-forming minerals, or common minerals that make up most of the rocks of Earth's crust. And there are only a few dozen of these minerals. The reason why there are only a few dozen is because they're composed mainly of only 8 different elements that make up more than 98% of the continental crust of Earth. So hopefully you're all a little bit less intimidated now that I'm saying that there are only a few dozen of these minerals, and that there are only 8 elements from that periodic table that make up more than 98% of the continental crust. So these are the 8 elements that make up most of the continental crust. As you can see, oxygen makes up almost 50% of the continental crust, and silicon makes up more than 1/4 of the continental crust. So as you'll see later in this lecture, oxygen and silicon come together to as part of the vast majority of minerals that exist. Other common elements in the Earth's crust include iron, potassium, magnesium, sodium, calcium, aluminum, and others. I guess it's important to note that aluminum is actually the 3rd most common element in the crust, and iron is the 4th. So, as I just mentioned, the vast majority of minerals contain silicon and oxygen, and this is because silicon and oxygen together comprise about 75% of the elements in the Earth's crust. And because silicon and oxygen are so common in Earth's crust, silicate minerals, or minerals that contain some silicon and some oxygen, actually account for greater than 90% of the minerals in Earth's crust. Alternatively, obviously, non-silicate minerals that do not contain silicon and oxygen are not as common, but they are pretty important economically and as geological resources. A few examples include iron, aluminum, gypsum, and also these minerals are major parts of sediments and sedimentary rocks, and we use a lot of different types of sediment, such as sand and clay, for different types of building projects and infrastructure, for example. This is a diagram of what a silicate is actually built out of. So the diagram on the left, in the diagram on the left, you can see a silicon oxygen tetrahedron. So this is actually the most basic building block. It's a compound that has one silica atom and 4 oxygen atoms. And this building block often combines into complex structures in minerals because, as you can see, the silicon oxygen tetrahedron has a charge of -4, and that -4 charge needs to be satisfied by positively charged cations, which are usually metals, and this -4 charge can be satisfied in a number of different ways using different structures of silicon oxygen tetrahedron. So speaking of silicate structures, on this slide you can see a number of different ways in which silicon oxygen tetrahedrons bond to one another to form these silicates. So the first example on the far left are independent tetrahedrons, and these are kind of what you think they are, where you have your simple silicon oxygen tetrahedron, which altogether has a charge of -4. And so the silicon oxygen tetrahedron is basically looking for some metals to bond to it that have a combined charge of +4 so that it can have a neutral charge. And then you can see type B, single chain silicate structures where the corner oxygen of the silicon oxygen tetrahedron is shared with another silicon oxygen tetrahedron. And then much more complex types of silicate structures like the double chain, sheet structure, and three-dimensional framework, where more and more of the oxygens of the silicon oxygen tetrahedron are actually shared with another silicon oxygen tetrahedron. And what having so many different types of silicate structures does is it means that you are left with a number of different charges, negative charges, that need to be satisfied by positively charged metals, and it allows for the formation of a very large number of minerals because different charges need to be satisfied in different ways based off of what the silicate structure is that the metals are bonding to. These silicate structures then can join together to grow silicate minerals or silicates. Most of the silicate structures, including the ones that we just reviewed on the last slide, have a net negative charge, meaning they are basically looking for other ions with a positive charge that want additional electrons to balance their charge and follow the octet rule. So generally these ions are metals because metals usually have a positive charge. So common examples of the ions that bond with silicon oxygen tetrahedra structures are iron, magnesium, potassium, sodium, aluminum, and calcium. So this has been a lot of information, especially for those of you that don't really have a chemistry background. So I'm going to kind of just review what I've gone over so far before I move on. So atoms of different types of elements bond with one another to form compounds. They bond through different types of chemical bonds. And ions are atoms or compounds that have a net electrical charge, meaning that they are not following the octet rule, or their valence electrons are not balanced. And so ions can have a net positive electrical charge, those are known as cations, or a net negative electrical charge, those are known as anions, due to having different numbers of valence electrons. And atoms and compounds want to bond with other atoms and compounds to fill their outermost electron shell with electrons, usually 8. That is the octet rule. But what you need to know is, for example, if you see an atom or a compound with a charge of -2, then it is looking for another atom or compound with a charge of +2 to get to a point where it has a neutral charge as a mineral. And minerals are formed when atoms and compounds bond with one another. One example of the types of bonds that form the vast majority of minerals in the continental crust are including the compound SiO4 or silica tetrahedron, and those can bond to other silica tetrahedra in a variety of ways, forming silicate structures, which kind of opens up the door to being able to form a very large amount of different types of minerals, which is how we can have 4,000 different types of minerals on Earth. So moving on to joining these silicate structures that we just spoke about to grow silicate minerals. So the covalent silicon-oxygen bonds in the silicate structures are typically stronger than the ionic bonds of the silicate structure, or the bonds between the positively charged metals and the silicon-oxygen tetrahedra. And these stronger bonds control the cleavage planes and the hardness of the minerals. For example, quartz has a three-dimensional framework as its silicate structure. And this three-dimensional framework makes it very hard, and it lacks any planes of cleavage or weakness because all of its bonds are covalent bonds. Conversely, you have a mineral like talc, which has a sheet silicate structure, and each sheet of the silicon-oxygen tetrahedrons is bonded to the other sheets of silicon-oxygen tetrahedrons by weaker ionic bonds. And that gives it a one-directional cleavage, and it makes the mineral very soft. Now moving on to talk about different types of silicates. So there are two major categories of silicates. There are the light silicates and the dark silicates. The light silicates are generally light in color, and they have a fairly light weight to volume ratio, or a fairly light specific gravity of approximately 2.7. And they lack the elements iron and magnesium, which makes sense because iron and magnesium are heavier elements. And these light silicates usually contain varying amounts of the lighter elements aluminum, potassium, calcium, and sodium. Conversely, the dark silicates are generally darker in color, and they have a heavier specific gravity, or weight to volume ratio, of 3.2 to 3.6, and they contain more iron and or magnesium, which are heavier elements. However, all of these silicates are common in Earth's crust. So this just shows number of common silicate minerals and the type of silicate structure that forms them. So on the top here, you can see olivine is an example of a silicate mineral that has the single tetrahedron structure. Pyroxene is an example of a silicate mineral that has the single chain structure, and so on and so on. I encourage you to read into this a little bit more in your text. On to the light silicates. So the first type of light silicates that we're going to talk about are the feldspar group. And this group is the most common silicate group and makes up more than 50% of Earth's crust. So it's extremely common, and it's good to understand and know about. The feldspar group forms under a wide range of temperatures and pressures, which is part of the reason that it's so common. And it exhibits two directions of perfect cleavage at 90 degrees. And its two most common members are orthoclase or potassium feldspar and plagioclase feldspar. And you will learn to identify both of those in the lab. However, here are just some examples of potassium feldspar on the top. And you can see the two planes of cleavage at 90 degrees on that, or the planes of weakness that the samples broke upon. And then on the bottom, you can see the plagioclase feldspar as well. The second most common type of light silicate is quartz, and I'm sure most of you probably know what quartz is. A lot of people that collect rocks collect quartz. And it's the only common mineral made completely of silicon and oxygen. So this is kind of the exception because of the three-dimensional structure of silicon and oxygen and how silicon is just bonded to two oxygens and it has a balanced charge. The silicon and oxygen didn't need to bond to positively charged metals in quartz. And this makes it hard and resistant to weathering. And as far as physical properties, the conchoidal fracture that it has, or the way that it sort of breaks like glass rather than along any cleavage planes, is kind of a unique feature about it that makes it fairly easy to identify. Differences in colors are formed by just small impurities in the quartz. So here you can see examples of those small impurities and how different quartz can look. So this is one that's definitely important to use properties other than color to identify. Another common type of light silicate is muscovite, and this one has excellent cleavage in one direction. So it breaks sort of along sheets, and the sheets are thin and clear. And if you're walking along the beach and you see glimmering and you think, oh, maybe that's a little speck of gold, it's usually actually a piece of muscovite. This is a muscovite sample here. And then also it's important to note that clay minerals are light silicates. In this case, clay is sort of just a general term used to describe a variety of minerals that have a sheet structure, kind of like muscovite does. And clay makes up a large percentage of soil in general. And most clays originate as products of chemical weathering of pre-existing minerals. Kaolinite is a common clay mineral that is used to manufacture fine dishware, for example. And this is a sample of kaolinite here. I believe that you'll identify kaolinite in lab as well. Moving on to the dark silicates. These silicates are, as the name implies, the sorts of minerals that you're more likely to find in darker rocks, and that you're more likely to find in basalt. And you may find some of these minerals in oceanic crust as well as continental crust. So the first one worth discussing is the olivine group. And these are high temperature silicates, meaning that these minerals crystallize they can crystallize from magma or lava at high temperatures. In this case, olivine crystallizes from magma. And the color is generally black to green. It has a conchoidal fracture similar to quartz, and it generally forms small rounded crystals. The next type of dark silicate is called the pyroxene group, and these are important components of dark colored igneous rocks. For example, basalt. Augite is the most common mineral in the pyroxene group, and it is generally black in color and has two cleavage planes at 90 degrees. And as I already mentioned, it's kind of the dominant mineral in basalt, and this is a picture of augite here. The amphibole group is also important, and all of these dark silicates you will be learning to identify in lab, by the way. Hornblende is the most common mineral in this group, and it has two perfect cleavage planes at angles of 120 and 60 degrees. A couple more of the dark silicates are biotite, which is an iron-rich member of the mica family. So if you recall, muscovite was a light silicate that is in the mica family. And this one, like muscovite, has one directional cleavage, so it sort of breaks off in sheets, kind of like muscovite as well. And then lastly, garnet. This one has a very unique color and luster and fracture, and it forms in a dodecahedron pattern, or a 12-sided crystal, which is very unique. All right, so we made it through the silicates. I know that was a lot of information, and I encourage you to go through these slides a few times and to review the text, and to focus on your mastering geology this week, because understanding the silicates and understanding minerals really is a building block to understanding all of the different types of rocks, and then later understanding all of the different physical and chemical processes that impact rocks and the entire world around us. Almost everything that's solid on Earth's surface is a silicate mineral. So that's important to note. They make up 90% of the crust, for example. Moving on to the non-silicate minerals just for a minute. The non-silicate minerals are divided into groups based on the negatively charged ion that the minerals in the group have in common. So non-silicate minerals that have oxygen in them are called oxides. Non-silicate minerals that have sulfate in them are called sulfides and sulfates. Or I should have said that have sulfite in them, sorry. And then you have the native elements. So some minerals are just the native element. For example, gold and silver. Those are minerals, and they're also elements, which is pretty interesting. And then you have carbonates, which we talked about earlier, are often from biological life that secretes calcium carbonate, and that can form the carbonate minerals. And then halides, which are like Halite is one example of a mineral in the halide family. And then phosphates that have phosphorus as the negatively charged ion. And so this figure shows the most common minerals that are carbonates, halides, oxides, sulfates, and native elements. And a lot of these you will be learning to identify in lab. And I encourage you to look into these a little bit more in your text. All right, everyone, that's everything I have for you on matter and minerals this week. I hope you got something out of this lecture. As I said, at the very least, what the difference between a mineral and a rock is. That's going to be important for you to understand going into the next lecture on igneous rocks. And it's also going to become very important for you to understand in lab, because you'll learn to identify minerals and rocks. And part of identifying rocks is identifying the minerals contained in them. And when you take your rock and mineral quiz, you need to know the difference. Anyways, I guess I'll move on to the igneous rocks lecture now. And hopefully either Jeff or Ander can give you a good lesson on how to identify minerals and later igneous rocks in the lab this week.